Hi everyone on Zoom. Can you tell me if you can hear me? Can you hear me? Yes, we can. Ok, c'est bien. Et là, okay, so on Zoom, can you confirm that you can see the screen? Yeah, okay, good. We can start then. Right, so it would have been nice if you could have come a bit closer instead of me having to speak so loudly, but yeah, maybe the last row, that would be good if you could come a bit closer. So last time we spent quite a long time seeing the principle of statistical testing, and so if some of you have already heard of it, so hopefully you will follow it quite easily, and it was a good reminder. For those of you who had never heard about statistical tests, it probably was a bit rough, but you'll see that now we're going to go into the detail of the different tests that I want you to be able to use. And as we go through the different tests, you should be able to, well, we'll be revising all those concepts because it's always the same principle. So now we're going to, today and maybe next time, we're going to go through different types of tests. So remember now, is this working? It's working on my screen, but not on the Zoom. Yeah. So, so if you remember last time, we said that the main steps of hypothesis testing are first to examine the question under study to correctly state the hypotheses. What question are we trying to answer? Then to define and state the null and alternative hypothesis. Choose a significance level, and you remember that we said it's often 5%, but not always. And obviously you want it to be as low as possible, but you have to be careful because if you lower alpha, you increase beta, the type 2 error, which means that you're decreasing the power of the test. So this is why we can't just put alpha to a minimum. And then determine which test to use. And so that's the main difficulty here for you, is what is the right test to use in each of the situations I am in. And depending on the test you're using, then you will know what the distribution of the test statistic is under the null hypothesis. And just to state again that under the null hypothesis is a mathematical way of saying if the null hypothesis is true. And once we know what the distribution of the test statistic that we're interested in should be under the null hypothesis, we will then calculate the observed value of this test statistic in the sample. And depending on where the observed value is in the expected distribution, we can then decide to either reject or not reject the null hypothesis, depending on where the observed value is compared to the expected distribution. And then, of course, once we've rejected or not the null hypothesis, we conclude concerning the test. So now we're going to focus on this graph which I said is basically all the main tests that you need to know about at the end of this course. And so what the main thing is, okay, there are lots of different tests, and how do we decide which test to use in each situation? So we will be seeing what the different tests are used for, and we'll be trying to help you to know how to decide where you are in that tree. So for the moment, today, we'll be looking at quantitative data, so the yellow, and then looking at differences between groups in terms of means. Okay, we'll be looking at means and variances, but this one is the means, and depending on whether there's one or two or more than two samples, we'll be using different tests. So today we'll be going over most of the orange bit, not ANOVA for the moment, and we'll be, for the moment, focusing on parametric tests, which are the darker squares, and then we'll have a lecture on the non-parametric tests, which are the pale pastel-colored squares. So how do you decide which test to choose? Well, as you can see, it depends on the type of variables involved, because you can see that the main question at the top is, what type of data are we using? Do we have qualitative data or quantitative data? So that's one of the main questions. Which variables are involved? What type of question are we asking? So that is very important, and it's not that easy. So when you get down to, doing your own experiments and going into a research question, it's often, and I can tell you when I speak to grown-up researchers and I say, okay, so what's your question? They often have difficulty phrasing it in a way that makes it possible to analyze the data. So it's not a trivial exercise. It's not easy. So we're going to obviously give examples, but the question number 2 is actually often quite difficult to say in a way that can transfer into a proper analysis. Now, how many samples are we interested in? 1, 2, or more? That is going to determine which test we use. And are the individuals paired or independent when there are 2 samples? And obviously, there are also lots of statistical mathematical assumptions which we need to check, in particular, whether distribution is normal, whether we have equal variances, and then if not, we have to use non-parametrical tests. So that's a kind of summary of how you have to choose the right test, but obviously we will go through that as we go. So for today, we're going to start work on, as I said, all those this bit of the graph. So we're going to work on means, looking at differences between groups in terms of means. I could add a means here, les moyennes, and we'll look at these first few squares. So when we have one sample, the easiest test to use is a student's t-test, where the test statistic looks at the mean minus a reference mean over the square root of s squared over n. So this is the observed mean, this is the reference value, this is the variance of the sample, and this is the size of the sample. And we compare this test statistic to the threshold value, le seuil, in a student distribution with n-1 degrees of freedom, or you look at the p-value, the degree of significance, and compare it to alpha. To do a student t-test with one sample, you need to check whether the variable that you're interested in follows a normal distribution. Have we done the lecture on checking? Yeah, we have, for checking for normal distribution, or not? Not yet. Sorry, I'm getting confused. What was the... No, we haven't done it yet, have we? No, okay, so we'll see that later. How do you check for a normal distribution? Okay, so first example, so we'll try in the lectures, we'll talk about the tests that we need to use, and then we'll apply it so that you can see how it's applied in each case. So first example, the packaging of a nutritional supplement indicates that the mean content in sugar, grams of sugar per gram of product, is less than 0.3 grams. In a randomly selected sample of 16 packets of this nutritional supplement, the observed mean content in sugar is 0.295, with a standard deviation of 0.168 grams. At the 5% significance level, so that means if alpha is equal to 5%, do you think the information on the packaging is correct? So look at this thing and try and write down for me what the null hypothesis and the alternative hypothesis is. What do you think in this case? What is the question we're asking? And one thing I want you to remember, which I think I said when I did the first lecture, is that for you, the null hypothesis is nearly always that a parameter is equal to something else, okay? So in your null hypothesis, you're talking about a mean or a variance or a proportion, and you're saying it's equal to something. And the alternative hypothesis is that it's different or less than or greater than. So if you have it'd be good for you to have, a sheet of paper or something next to you. So you read that and think, okay, if that was my experiment, with the question that's asked, what is the null hypothesis? What is the alternative hypothesis? And try not to cheat, because every time I ask you a question, the next slides give the answers. So if you want to benefit most from the, the more you think about something, the better you'll remember it. So you have a think about what you think the null and alternative hypotheses are. Just a few minutes, seconds. Dans le M2, vous êtes combien? 17. Et le M1? Ah, là, vous êtes clairement pas 48. Non, mais c'est pas grave, hein. Non, mais je sais que vous êtes, j'aurais dit à peu près de 50. Donc ça, je savais, si le M2, je savais pas combien. I think many people have thought, okay, I know about stats, so I'm not coming to these lectures. That's okay. We'll see what happens at the end. But there are bits which are repetitive for some of the Masters 1 course, as I explained in the beginning. So have you thought about what the null hypothesis is? What do you think? Can someone tell me what they think the null hypothesis and the alternative hypothesis are? Would you like to tell me? So you'll have a go at telling me what you think the null hypothesis and alternative hypothesis are. In French, if you want. L'hypothèse nulle, l'hypothèse alternative. Pardon, j'ai pas entendu juste avant. Okay. Special hypothèse nulle? Is that so? Just repeating, the null hypothesis is that the mean content to sugar is less than 0.3 grams. Does everyone agree with that? Or not? What did you say?
0, c'est pour l'égalité, du coup, ce serait dire que 0 sur 295, c'est genre c'est égal à 0,3.
Voilà. Voilà. I said just before that the null hypothesis is equal, always an equal sign, and the alternative hypothesis is different or less than or more than. So do you want to start again? So the null hypothesis is voilà. C'est égal à 0,3, yes, equal to 0,3, and the alternative hypothesis? Okay, so often, listen, often what you want to check, or what you hope is true, is what goes in the alternative hypothesis, okay? But it's easier, not always, because it depends what your question is. But so it's easier for you to remember, as I said, as a general rule, so there are exceptions, but for you, as a general rule, the null hypothesis has an equal sign, and the alternative hypothesis has a different less than or greater than sign, okay? So, yes, that, because the question is, do you think the information on the packaging is correct? What it says on the packaging is that there's less than 0.3 grams of sugar. And so we want to check, is that true or not? And then we decide that, yeah, the null hypothesis is mu equal, so mu being the real quantity of sugar in all the infinity of packets available. The mean quantity of sugar is 0.3. Oh, sorry, there's a mixture between commas and points, but this is the same, okay? Yeah, French, English, just mixing it all up. And the alternative hypothesis here is mu less than 0.3. So often when you go through the lecture, you think, okay, you remember I said the alternative hypothesis can be either different, less than, or that's the bilateral one, or less than and more than. And students often say, I say usually we use the bilateral. That's true. Usually we use the bilateral, but sometimes not. And when do we use the less than or greater than? When the question is explicitly saying something about less than or greater than. Okay, so here we know there was a question about that. Is the quantity of sugar less than 0.3? So because the sample is a size less than 30, we can't use the Z test. The Z test is what I used as the example in the general lecture last time. I said we can use a Z, do you remember? But most of the time, well, if a sample's too small, you have to use a t-test. T-test is what I showed you there. And if you look carefully, you'll see that this formula is the same as the Z. Okay, it's the same formula, but which is because when the samples are very big, the Z tends towards the T distribution, student distribution tends towards a Z distribution. So here, because the samples are small, we will use a student distribution, and we have to check whether the variable we're interested in, which is the quantity of sugar, follows a distribution. So for the moment, we haven't seen the lecture, so we can't check it, but it says in the question, the quantity of sugar is assumed to follow a normal distribution. So that means we can assume it is true. So we can use this test. So here we calculate the observed test statistic, the observed value of the test statistic, which is the observed mean, 0.295, minus the reference value. So this is the reference value, the mean, which is true for the null hypothesis, so it's 0.3. And then here we put the variance, which was given here. Well, it said standard deviation equals 0.68. Come closer. It's okay. Come closer so that you don't. Yeah. At the 5%, so that was the standard deviation. So you have to be careful when you're given exercises. Is it talking about the standard deviation or the variance? So here, because we want the variance, you have to put 0.68168 squared equals 16. We find this value. So for a significance level of 0.5%, what is the threshold. So the threshold is found by looking at the student distribution for 15 degrees of freedom. N is the size of the sample, a sample of 16 packets. And so here, 15 degrees of freedom, 5%, we can look at the table of the student distribution. So it looks like the normal distribution, but remember I told you at the beginning that they're very close, but they're not identical. So you find the degrees of freedom. This is how you read the table. So we said 15 degrees of freedom, DDL, degré de liberté, or degrees of freedom. And so this is the line giving us the threshold values for some values of alpha for a unilateral test, okay? So we want to know what is the value, the threshold, for a 5% alpha equals 5%. And yes, sorry. Alors, si, look, 0,295 is the observed value in our sample. Okay, so did you see that here? This is 0,295. It's the observed value. So you are confusing. In the null hypothesis, we want to know whether something is true. So the question we're asking is the packaging, we're saying for all the packets, for the millions of packets of cereal, there should be less than 0.3 grams. So this is the reference value. So that is your hypothesis, you see? And then we observed in 16 packets a mean of 0.125, 295. Do you understand? So it's different, yeah. But good question. So here, yeah, so what we're now doing, if you remember the reasoning behind the test is, I'll try and stay at the book here because we'll run out. But you remember we said, so what we're saying is that if the null hypothesis is true, si l'hypothèse nulle est vraie, then the distribution of the test statistic of this test statistic should be a student distribution with 15 degrees of freedom. And we found a value of minus 0.119. So now we need to know, what are we expecting? Where is it in this distribution? Is it in the very rare areas, or is it a normal value for this distribution? So we look for the value corresponding to 5%, and we see 5%, alpha equals 5%. The threshold is 1.753, but you see this is on the positive side, and we are looking at the negative side because we're looking at mu less than 0.3. So we just take the negative because the student distribution is symmetrical, just like the normal distribution. So that means our threshold is minus 1.753. And we can see that this observed value, minus 0.119, is, so compare this to the threshold here, and we can see that it is greater than, which means we can't reject the null hypothesis. So if we do not reject the null hypothesis, we cannot confirm that the content in sugar is lower than 0.3 grams. So I am still going to write on the board because I find it easier to explain that way. I got a P. So do you, so is the reasoning clear, or do you want me to re-explain it? So here we said that is the reference value. We said we're going to look at null hypothesis. So it's a unilateral alternative hypothesis. We say if H0 is true or under H0, then the test statistic, which we're interested in, T equals M minus our reference value over square root of this should follow a student distribution. Okay. And we found, okay, so this is the student distribution. And we found that the threshold that corresponds to 5%, alpha equals 5%, is minus 1.73. And the value we found here is this, which is here. So we are closer to the middle. So do we reject the null hypothesis when we're in the extreme values, okay? This is reject H0. This is do not reject, because when you're here, you're in the expected values. So what's a little bit stranger in the unilateral case is that you just don't care about these extreme values. You're only focused on that because we're using the unilateral alternative hypothesis. You can see that this value which we found is in the expected values for something which is following a student distribution. So we do not reject, because we're here, we do not reject H0. The value we found is consistent with what we expect. So if we do not reject the null hypothesis, we do not reject it, it means we can't confirm that indeed the packaging, indeed we have less than 0.3 of sugar. Do you understand the reasoning? Oui? Yes? It's called degrees of freedom, degré de liberté, and it's to do with the size of the sample. So it's the size of the sample minus 1. And what it means mathematically is a bit complicated to explain, but basically it's the amount of information we have. So we have 16 observed packets, and we deduce a number, 1 or 2, depending on how many parameters we estimate. So it's always the same. When you're doing a one sample t-test, it will always be n minus 1, which is the size of the sample minus 1, okay? And when we look at other tests, sometimes it will be degrees of freedom n minus 2, but I'll show you. See? So it's to do with the distribution, and it's to do with the size of the sample, okay? Oui. It was calculated here. Well, you look at where it is in the distribution. You look at where it is in the distribution, and you just see whether it's closer to the expected values. So remember that here, this is how often the values happen. The distribution means the probability that t is equal to minus 0.119. This is probability, and it's quite high. So it's consistent with what we expect. Whereas seeing minus 1.7 is not very common, and it's even less common to see minus 2, etc., etc. You understand? So what we found in our sample is consistent with a distribution, student distribution, which means it's consistent with the null hypothesis. Donc, on ne rejette pas l'hypothèse nulle, because it's consistent with the null hypothesis. Okay?
Genre le 0,79, il est compris entre 0,3, moins 0,3 plus 0,3, c'est ça?
Non, moins 0,119 est supérieur à ce seuil. Et voilà. Il n'y a rien à voir avec 0,3 moins 0,3. This is the hypothesis.
Ah, ok, donc si la valeur de 0,79 se trouve dans cet intervalle, ça veut dire qu'on ne rejette pas les voilà. Tout simplement.
Voilà.
Okay.
Yeah. Oui. Alors, j'ai écrit, pardon. The whole sentence is, if H is true, then this should follow a student distribution with 15 degrees of freedom, which means that, well, with a 5% significance level, 5% of the value should be less than 1.7, and 95% of the value should be here. And we found a value which is consistent with that. So we do not reject the null hypothesis, because what we see is consistent with the null hypothesis. Does everyone understand? So as we go along, you'll see it's always the same thing, but I take time to explain because it takes time to understand it for everyone. Okay, that's why I think that even for M1 people, it's useful for you to come back and listen to it, so you can tell your friends. But you know, yes.
Là, on va retenir 1,7%.
Oui.
Ça, c'est jusqu'à l'infini.
For un test unilateral, for a unilateral test, because but you remember last time that if we were in a bilateral test, we would have a value here, and we would say you have to be there. But because it's unilateral, we only look at this side. Okay, that's the difference. If it was, so we only look at either reject or do not reject. Whereas bilateral, we had different here, then we would have two values here because we would exclude 2.5, 2.5, and then we would say do not reject is here, do not reject null hypothesis, and reject is here and here. That's the big difference, important difference between a bilateral and a unilateral.
Ça, c'est systématiquement. Voilà, toujours vers la droite.
No, because we've had this
Dans
one.
le cas, s'il est unilatéral.
Mais après, we could have had unilateral the other way. Si on avait H1 mu supérieur à 0,3, là, on aurait fait là, et ça aurait été reject. Voilà. Ouais. Is it clear for everyone? We go to the next example. So off we go. Now, hello. So next slide. Right, so that was the first example. And if we want to talk about outputs, then, you know, normally with, if you're using software, which is more common, then you will not necessarily know the value moins the threshold value. What you will have, so this is the same data, 16 observations, sorry, 0.295 of mean, a confidence interval for the mean. Here we have the t that we calculated, minus 0.119, 15 degrees of freedom, but we don't have the threshold. We don't have le seuil, 1,753. What they do give us is for each null hypothesis, you see mean less than 0.3, mean different, ça veut dire différent de, or mean greater, we have the p-value, le petit p. So now, do you remember how we said, how do we calculate? If I just go back and open last time's lecture, just for one thing. Yeah, here, not that one. General principles. So if you just remember this one, if you just go back to this, remember I said, when you want to know whether we reject a null hypothesis, either we do what we've just said, okay? Or remember, we look at the p-value here, okay? In that case, if you look at the p-value, you say, is p less than alpha? Then I reject. Or is p greater than alpha? Then I do not reject. So it's the same idea, but we're looking at the areas here. We're looking at the areas, the red and blue areas, instead of looking at these values. So here, if I go back to what we're looking at, if we go back to this, then we see that the p-value here is 0.45, which we compare to what? To alpha, which is worth 5%. So here, is p greater or smaller than alpha? Greater, 0,45, c'est plus grand que 0,05, oui. So we do not reject the null hypothesis because I'm going to write it in red, okay? If this is always true, unilateral or not, if P is less than alpha, reject H0. If P is greater or equal to alpha, do not reject, okay? So it's equivalent because P, here we said P is this, you see? P is the area under the curve. This is P égale 0,45. We have alpha here, which I wrote here. Not very well, but we knew that alpha here was equal to 5%, so 0.05. This is alpha. Okay, this is alpha. P is bigger. So we are in P greater than alpha, so we do not reject. Okay? Yeah? Right. So every time there's two ways of doing things, okay? Right. So now if we keep going, now we're going to look at comparing two means, not just one sample compared to a value, 0.3, but comparing two means. So we said before, the choice of test depends on the type of variables, the assumptions and not the assumption, and the number of samples. And there are two, if we have two samples, two means, then there are two possible situations. Either the samples and the populations are independent, or they are paired, okay? So what does it mean, independent and paired? Independent means the measures were made on different individuals, and paired means the pair, okay? It means we doing measures on the same individuals at different time points. So if I give some examples, if we have a sample of smokers randomly drawn from a population of smokers and a sample of non-smokers randomly drawn from a population of non-smokers, then these two samples are independent because you can change during your lifetime, but at one moment in time, you're either a smoker or a non-smoker, okay? And if we have some mice treated with a molecule A and some different mice treated with a molecule B, we have independent samples. But if we have a sample of individuals and we measure their glycemia in, so a sample of 100 individuals, we measure the glycemic index, and then 6 months later, we measure the glycemic index again in the same individuals. So you have two samples, you have 100 values here and 100 values there, two samples, A and B, but on the same individuals. And so there is a link between the values at two different times, because if I measure your pulse now, and I measure your pulse in 10 days' time, there's a relationship, there's a correlation between the values. They're not independent. And so in statistics, all the statistical testing is based on independence. Independence is an important assumption. So when you're not independent, you have to do things differently. So we have different tests for independent samples and paired samples. So here, imagine we have a team of surgeons who wish to compare two different techniques. Laparosurgery, I don't quite know how you say that, okay? Technique 1, and a standard surgery. So a new surgery and a standard surgery, technique 2. There are 36 patients, 18 of them will have this type of surgery, and 18 different ones will have the standard surgery. And just parenthesis, we could have 10 and 26. That would still work. The test would still work. But here we had half and half, okay? And so here we're looking at the length, the duration of the surgery. How long did the surgery last? 60 minutes on average for the 18 patients. You measure each surgery, how long did it last? The mean here was 60 minutes, and the standard deviation of the duration of the surgery, la durée de l'opération, was 4 minutes. And here it was 75 minutes with a standard deviation of 5 minutes. And the question is there a significant difference in the length of the surgery between both techniques? So is one technique longer than the other? So same question as earlier, write down the null hypothesis and the alternative hypothesis. what do you think the null H0, the null hypothesis is, and what do you think the H1 alternative hypothesis is? And this is a very important step of knowing how to do tests, okay? And remember what I said, usually there's an equal sign in the null hypothesis. So I'm helping you quite a lot. So what do you think the null and alternative hypotheses are?
The null will be that there will be no significant difference in the length of the surgery between both techniques.
Sorry, can you say that again? Thank you for...
Yeah,
go ahead.
The null will be that there will be no significant difference in the length of the surgery between both techniques.
Yeah.
And the alternative will be, or the H1 will be that there is a significant difference.
Yeah, that's right. So we can write it. So I'm repeating for everyone here. H0 is mu, is the real mean of the duration of the first type of surgery is equal to the real mean duration of the second type of surgery. So as you say, there is no significant difference, but the hypothesis, you can just say it's equal. And the alternative hypothesis, sorry, is that there is a difference. So here, I was just talking about the general case again. So if I go a few slides later, in the example, you're right, this is the null and the alternative hypothesis. Now, I'd just like to repeat, I say it, and students kind of hear it, but they don't realize what it means. You see here that I say mu1, mu2, they're just names, okay? But realize that mu1 and mu2 are the true mean lengths of the surgery, which means you're not saying that the null hypothesis is M1 60 equals 75, because you don't need to do a statistical test to know whether 60 is equal to 75, okay? So please don't write, if I write that in an exercise, please don't write that H0 is M1 equals M2, okay? Because that's wrong, that doesn't make any sense. Mu1, remember my initial slides in each of my lectures, that we're talking about a sample. We've just got 18 patients here and 18 patients there, but we want to say something which is true about all those surgeries if we operated millions of people. So always remember that the hypotheses concern the population, and then the test is on on the sample. So that's right. Thank you, Zina, for answering. It's good to know that you're all there. And so I'm just going to go back a few steps to explain the general, and then we'll go back to the example. So when you're comparing two means in the case of independent samples, if the distribution of the studied variable is normal in each of the populations, and if the variances, the real variances of the variable we're interested in, so here, for instance, the duration in minutes of the surgery, if the variance in the population are equal, then you can use a student t-test for independent samples. And so these are the different possible hypotheses, null hypothesis, and three possible alternative hypotheses, either different, greater, or less than. And so this is, in red, is the general formulae. So you can calculate a test statistic which looks at the distance between the observed means divided by a common variance multiplied by 1 over n1 plus 1 over n2. So these are the it's a linear combination of the sample variances. And here we have n1 plus n2 minus 2 degrees of freedom for the student distribution. So you see it's not always the same degrees of freedom, but every time you have a test, in the general formula will always be, for that test, those degrees of freedom, okay? And it's always to do with the sample size. So when there's one sample, it's n minus 1. When there's two samples and you're comparing means, it's n1, the size of the first sample plus the size of the second sample minus 2. And we have to check two things, whether the distribution is normal and whether the variances are equal. So we will see that there is a test to check that the variances are equal, and we will have also a lecture on determining whether a distribution is normal. And then, as usual, you reject the null hypothesis if the observed value of the test statistic is greater than a threshold, or if the p-value is less than alpha. And then if you've got different alternative hypotheses, you have to rewrite, but it's always remember this thing. So if you, so just write down maybe those. 18 patients, M1 equals 60, M2 equals 75, S1 equals 4, and S2 equals 5, and try and calculate this T0. So you have to first calculate S squared and then T0. So, yes? The degrees of freedom. No, it's not equal to the number of samples. It's equal to the size of the two samples minus 2. N1 plus N2 minus 2. With another test. Ah, non, moins, ouais, en fait, non. Moins 2, c'est moins, it's minus the number of parameters which you have already estimated. But you don't need to remember that, because every time we use a test, I will say, with that test, c'est n-1. Avec ce test, c'est n1 plus n2 moins 2. Si j'ai mis moins 2, c'est que c'est toujours moins 2 dans ce type de test. Okay? Non, parce que c'est encore un autre type de test. Okay. This is just the test for two independent samples. Okay? When we have more than two samples, we will use another test called ANOVA, and that's different. Yeah. So try and calculate this based on the values here. M1 equals 60, S1 equals 4, M2 equals 75, S2 equals 5, N1 and N2 are equal to 18. And you can do these calculations, okay? So did you find the values?
$9.93.
Okay. Is it, yes? Wait, someone here is also, yes, you have a question or just a minute, Zaina? Yeah. So S carré, you have to calculate it first. It's just underneath. C'est bon? Ouais. Okay, so Zaina, thank you for answering. So what did you find?
9.93.
Yeah, that's right. So first, maybe you can give us the value of S squared. So S squared is 20.5. Okay, so you calculate the common variance using this formula. So size of the sample minus 1 times that variance, etc. So just to note again, please note again that N1 and N2 do not have to be equal. They can be different. Here, N1 is equal to N2, but we could have different size groups. It works also. So 20.5, and then you are right, Zaina. The value is minus 9.94. So is everyone okay with that calculation? Yeah? And so then how do we decide whether or not we reject the null hypothesis? We have to look, we have to find the threshold. So here, do we have a unilateral or a bilateral alternative hypothesis? Hypothèse alternative, est-ce qu'elle est unilatérale ou bilatérale? Qu'est-ce qu'on a dit? On a dit bilatéral. We said bilateral. We just said there is a significant difference in the length of surgery. If there is, we just said there's a difference. If, for instance, the question had been, we want to show that the new surgery is shorter, then if the question is we want to show it is shorter, then you make an alternative hypothesis, which is mu1 is less than mu2, for instance. Okay. So here we just said it's different. So we just need to find the threshold. So how do we find the threshold? For a student distribution, the number of degrees of freedom here is N1 plus N2 minus 2. So 18 plus 18, 36, minus 2 is 34. And then be careful with these tables. So you can find different tables if you look on internet or if you have books on statistics. Some tables are like this. That's what you need to look at the drawing with unilateral. They're telling you just the unilateral values. And some tables are bilateral straight away. So this table is unilateral, which means because we only get one side, we have to look for the alpha, which is equal to 2.5. So listen, I will explain. We are in the case where we're interested in a bilateral hypothesis, okay? We are in a case where we're interested in a bilateral hypothesis, yeah, bilateral. So we want to exclude any extreme cases on both sides. So if alpha has to be equal to 5% altogether, we want to exclude the 5% most extreme values. So we have to exclude 2.5% here and 2.5% here. And student is symmetrical, just like the total distribution. So we need to find the value which corresponds to 2.5%, and this will just be the opposite, okay? So this is why we're looking for alpha equals 0.025, because this only gives one side. So if you look at 5%, it will be like looking for 10, do you understand? So here, the value for 34 degrees of freedom, we don't have 34, we have 30 and 40. So we say, so you're thinking, what am I going to do? But you can see that as the numbers get bigger, there's a smaller and smaller difference between the numbers, because when we get to infinity, these numbers, do you recognize 196? Do you remember 196 when we had a 5% level? It's the normal distribution number, because I told you right at the beginning that the student distribution tends towards, tend vers une distribution normale. So the bigger the N, the closer you get to a normal distribution. So here you can see that they don't write 31, 32, 33, 34 because they're very close anyway. So it means that our threshold is around environ 2.03. Okay, so here we write 2.03 minus 2.03, which means that when will we reject the null hypothesis and when will we not reject? We're going to say, where is T0? Where is it? The one we observe in our sample. So when do we reject or not reject? If I'm here, do I reject the null hypothesis? If I'm here, do I reject the null hypothesis? Okay, do you understand? So what is your T0? What did we find? The absolute value of T0. We look at the absolute value. Yeah, so where is it? Right over here, right? 9,93. So do we reject the null hypothesis or not? Yes, okay. We very strongly reject the null hypothesis because we can see that we are a long way away from the real value. On Zoom, can you hear me if I write things on the board? I know you can't see, but can you hear?
Yes.
Yes, good. Okay, I try not to, I need to try and turn the camera again, but yeah, anyway. So, because it's a bit complicated in this room. So, so here we reject the null hypothesis. So this is what I wrote here, okay? We can see that T0, 9.94, is greater than the threshold value, which is around 2. There is a significant difference in the length of the surgery, depending on the technique used. And if we look at the output of the software, so here it's the exact same data as the exercise. You see mean 60 and 75 with 18 observations in each group. And it gives you the T equal 9.94. And here for the alternative hypothesis with the difference in mean different from 0, so that's the same as saying mean 1 different from mean 2, or mean 1 minus mean 2 different from 0 is the same. You can see that the p-value is very, very, very small, okay? So is it less than 0.005? Yes. Okay, c'est plus petit. Le petit p, the area under the curve, is much smaller than 5 or 2.5%. 5%, sorry, so we reject the null hypothesis. It's the same conclusion. Do you have any questions on this exercise? Yes? Okay, good question. Good question. Why did we take the absolute value of 993? Because when you are in a bilateral case, you always take the absolute value. Is that what you wanted to say? Good. Yeah. So if you are unilateral, you leave it as it is, if it's negative or, but if it's the bilateral hypothesis, then you take the absolute value. Do you have any other questions? Is it okay? Right. So now we move on to, so we've done, so far, if we go back to this graph, we have done this one sample t-test compared to a theoretical value, 0.3 it was for us, but it could be something else. Then we've done 2 samples in the case where it's independent, and you can see the little stars are to say the conditions, the assumptions. So red star means it has to be a normal distribution, and we'll see how to check that. And green stars means you have to have equal variances, and we will also see how to check that. For the moment, we just did the test. And now we're looking at what happens if the 2 samples are not independent, like these patients were operated, these patients were operated, but paired samples, okay? So we're looking at this, and we use a different test, which is called a paired t-test. So, here is the example. We have a treatment which aims to reduce blood pressure, and it is tested on 10 patients. So the systolic blood pressure is measured before and after the treatment is given. And we look at the difference before minus after. So blood pressure before minus blood pressure after, which is calculated between each pair of measures. So it's the same 10 patients measured there. So we have 10 measures before, 10 measures after. And why are they paired and not independent? Because it's the same patient, okay? So you can transpose it to other situations. Every time the same mouse or the same sample, which you analyze with two techniques, every time there's that, then you're not with a condition of independence. And so you have to do things different. So the question here is, at the 5% significance level, is the treatment significantly efficient? So read the question carefully, write the null and the alternative hypothesis. Read the question carefully and tell me what the null and alternative hypothesis is here. You can call them before and after to give them names. So the mean before, the mean after, and decide what the null and alternative hypotheses are. Yes?
Qu'est-ce que ça veut dire X? C'est quoi?
C'est juste X, enfin c'est parce qu'il y a 10 individus, c'est X1 before, X2 before, X3 before, parce qu'il y a 10 mesures.
Après, avant quoi?
Le traitement, there's a treatment in the middle, if you read what it says. So read carefully what the question is. Is the treatment significant? So what is the null and the alternative hypothesis?
So we can say like H0 is the treatment, the blood pressure before is equal to the blood pressure after.
Yeah, that's very good. That's the null hypothesis, yes.
And H1 is the blood pressure is higher before the treatment than after.
Good. Does everyone agree with that? So null hypothesis, I haven't changed since the beginning of the lecture, is equal. So you can call it mu for mean. Okay, the mean blood pressure before is equal to the mean blood pressure afterwards. And that's the null hypothesis. And the alternative hypothesis is the treatment is efficient. Now, the treatment is efficient. What does that mean? Mathematically, if the treatment is supposed to reduce the blood pressure, then you would expect the mean before to be greater than the mean after. So is this a unilateral or a bilateral alternative hypothesis? Unilateral, okay? And the same as before, how did we know that we had to use unilateral? Because the question doesn't just say, is there a difference in the blood pressures? It says, was the treatment efficient? Okay, so that's how we know. So often students say, how do we know? Thank you, Yamina. And so that was the right answer. So now, same as before, I'm going to give the general way to do it, and then we will look at the example. So I said, for the moment, you might be thinking, okay, well, that is very much the same as what we did for independent samples. So what is the difference in paired samples? So first, you're going to see that instead of looking at the two samples, we're going to look at the differences between each pair. So we're going to look at the pairs of values. I told you that the fact that there was no independence was important. So in fact, instead of looking at these values, the before values, and then separately the after values, we're going to calculate the difference in each pair. So we're going to do before minus after for the first patient, before minus after for the second patient, etc. Okay? And so then we will have 10 differences, and we can calculate the mean of these differences, and we can calculate the variance of these differences. Okay? And instead of working with the mean, we're going to work with the difference, the means of the differences and the variances of the difference. Okay. So, and so the conditions are on the differences. So the distribution of the differences needs to follow a normal distribution. And then we can use a student t-test for paired samples. So I didn't lie, the null and alternative hypotheses that you said were correct. It was mu1 equals mu2 and mu1 different to mu2, but you can see that you can write that relative to 0. So you can say that's the same as mu1 minus mu2 equals 0, which is the same as mu of the difference equals 0. And this, therefore, you can write the alternative hypothesis as mu of the difference is different to 0. That would be a two-sided or bilateral alternative hypothesis, or you can do greater than 0 or less than 0. So, of course, maybe you're wondering, why did I do before minus after? You can decide to do after minus before, but in that case, obviously, it changes the sign of the difference which you are going to look at. Do you understand? If we do before minus after, and we think the treatment will reduce blood pressure, we expect the mean difference to be what? Positive or negative? Positive, yeah? Everyone understands? If I decided to calculate after minus before, I can, but then I would say then the difference has to be negative, okay? So that just depends on how you write it. So, and so what we can notice here is that, remember, if we go back to the first example with the cereal, we had one sample and we were comparing it to a theoretical value of 0.3, remember? And here, what are we doing? We have one sample of differences and we're comparing it to a reference value, which is 0. So in fact, this case is the same as comparing one mean to a reference value. Once you look at the differences, it's as if you only had one sample and you're comparing it to the reference value. So here, this test is the same as what we had before. So look at this formula, T0 equals mu divided by square root of variance over n. This is the same as, it's the same as that with mu, the reference, the reference value equal to 0. You see, it's the same formula. Mu md divided by variance of the standard deviation sur n. This is the same formula with mu equals 0. Okay, so it's the same. That's just so you notice that student t-test with paired samples is the same as comparing one sample to a reference value. And then it's the same as usual with a student distribution of n-1 degrees of freedom. So just to say again, the degrees of freedom always depend on the test situation. So you just learn the degrees of freedom for that test situation. And also, just to remind you again, you do not need to learn formulae off by heart, okay? I will give you a thing with, this is the formula for that, this is the formula for that, voila. You have to understand. So, and we need the differences to follow a normal distribution. So now, if you go back to that, can you calculate for me the test statistic for this exercise? What is the test statistic? You need to calculate this, okay, with the values for MD and SD, which are here. MD is 1.5 and SD squared is 3.85. Have you found the values?
2.42.
Yeah, has anyone here found the value? What did you find? Good, you agree. So yeah, so here is just to write it again. Mu before equals mu after is the same as mu d. Mu before minus mu after equals 0. Mu d equals 0. Mu before greater than mu after, mu d greater than 0. So 2.442, we need to look for the significance level. And remember, this time again, we are in a unilateral case. Number of degrees of freedom is 10 minus 1, so 9. So we look at line 9. We find 5%. So why are we looking at 5% and not 2.5 this time? Because it's unilateral. Good. So 1.83 is our threshold value. And here we found 2.42. So 2.42 is greater than 1.83. So we reject the null hypothesis. So the systolic blood pressure has significantly decreased between the first and the second measure. So the treatment seems to be significantly efficient. And if we look at the p-value, the p-value for the mean greater than 0, mean of differences, is 0.02. So is this p-value less than or greater than alpha?
Yes.
Less, okay. P is less than alpha, so we reject the null hypothesis. We get the same conclusion. I just want to, so here's a summary for the t-test for independent sample and t-test for paired samples. I just want to draw your attention and explain about calculating this. How do we get mu of a difference and standard deviation of a difference? So it's not complicated, just in case some of you suddenly wonder how it's done. So so here we have 10 values before and 10 values afterwards. So basically, give me a blood pressure that's not too ridiculous. 92 or something, I don't know. Okay. So we have patients 1, 2, 3, 4, here. And we have, say, 95. Is that a good blood pressure? Yeah, whatever. Then he has 92. So here they have the treatment. He has 95 before, 92 afterwards, 103, 104, 86, 80, 96, 97, 98, and here 81, 81. Okay, so now when I look at the differences, I create the difference before minus after. So what do I get here? 3 minus 1, 6 minus 2 and 0. Yeah, you agree? Then here I can calculate the mean of these differences. Tac, 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 divided by 10, I get a value, and the standard deviation or variance of the differences. Now, just as an indication, if you do the mean of this, or M1, I'm going to call it MB, and the mean of this, M afterwards, then you will find that MB minus M afterwards is equal to the mean of the difference calculated that way. It works. Okay, you can show it statistically speaking. So you could do the mean of this minus the mean of that. You will find the same MD. Okay, but then for variances, it's a bit more complicated. So it's better to do the differences that way. So that's just in case you have to do it at an exam. Okay, so the mean of differences is the same as the difference of the mean. La moyenne des différences, c'est la même chose que la différence des moyennes. C'est ça que je suis en train de vous dire. But the easiest is to first calculate all the differences and then do the calculations. Right, any questions on that? Yes?
statistique, si on a un flux statistique qui est négatif, on fait toujours la valeur absolue pour prendre le positif. Ou c'était juste.
Dans le cas d'un test bilatéral. Mais si le test est unilatéral, dans ces cas-là, ça dépend de si on est sur de l'inférieur, il faut le laisser en moins, ou du supérieur. D'accord? Enfin, dans le cas d'un test unilatéral, on met pas de valeur absolue. C'est que dans le test bilatéral. Right. So, so now we've looked at the means. So we've looked at the means. If I go back to my this one, okay. So we've looked at one sample, two sample independent t-test, two sample paired t-test. We will look at the ANOVA later on because that's a bit more complicated. And now we're going to look at differences in variance because we're just going to look at the two sample differences in variance, this one called the Fisher's test, because as you can see, comparing variances, equal variances, these green stars, are a condition to be able to do a t-test. So it's useful to be able to know how to compare variances, okay? So we're going to do that, learn how to do a variance comparison test. So remember that, what is the definition of variance? So first, the variance is the square of the standard deviation. And what is the standard deviation? The square root of the variance. So suppose you have a population of n individuals where the values of the random variable are x1 to xn, and you draw a sample, a random sample of size n within that population. So what you need to remember is that the variance is a way of seeing how much a sample of values, how spread out it is, okay? If you have a large variance, that means the values are very spread out. If you have a smaller variance, it means they're squashed together around the mean, because this is what you're looking at. You're looking at the mean distance between each value and the mean, okay? That is what this variance is about. C'est l'écart moyen de chaque point de l'échantillon avec la moyenne, ou de la population ici. When you're looking at the sample, the formula is slightly different because you estimate the mean. This is not the real mean, it's an estimated mean. You divide not just by n, the size of the population, you divide by the size of the sample, minus 1. So that's a form of degrees of freedom. It's the number of observations minus the number of estimated parameters. So these are the estimated parameters. So when do we need to compare variances? Because most of the time when you think of comparing things, you want to compare the mean. Why would you want to compare the variances? Well, sometimes you're interested in comparing the variability of a variable in two populations. So how precise, the precision of two types of measure. Sometimes you can be interested in the variability, and you want to compare the variability between two groups. And sometimes it's because you want to check the assumptions in order to do another test, which is what we were talking about. In order to do a student t-test or an ANOVA, we need to check whether the variances are equal. And the property of equality of variances is also called homoscedasticity. And if the variances are not equal, it's heteroscedasticity. But you can just say the variances are equal or not equal. So, same as usual, we have two populations. We're interested in their variability, their variances. We draw samples and we have the observed variances that are an estimation of the real variances. So here, the null hypothesis is not going to be equality of means. It's going to be equality of variances. Or you could say equality of standard deviation, but classically you look at the variances. And then the same, you can have alternative hypotheses that are two-sided or one-sided. And then we have a test, Fisher's test, which is used to compare two variances. The thing about this test is that depending on the alternative hypothesis, the test is slightly different. So in all cases, the test statistic is the ratio between the two variances, the two observed variances, okay? It's either S1 squared over S2 squared or S2 squared over S1 squared. But how do we know which one to put over the other? So the formula is quite easy, but it depends on the alternative hypothesis, which way round we put it. So if your alternative hypothesis is that S1 squared is greater than S2 squared, remember this is the null hypothesis, hypothèse nulle, this is the alternative hypothesis, then you put the corresponding estimated variance on the top numerator. If the alternative hypothesis is one-sided this way with the S1 squared less than S sigma 2 squared, then you put this S2 squared on top. And if it's an bilateral two-sided alternative hypothesis, then you look at the real observed variances, the observed variances, and you put the biggest one on top, okay? S2 is bigger, so you put it on top. S1 is bigger, so you put it on top. And in fact, here you see that you're also putting it in the same order with the supposed larger variance on top. So the test statistic is always the ratio of the two observed variances, but you have to look at the alternative hypothesis to know which one you put on top. So, first example, a biological measure based on blood samples is done either in a specialized hospital or in a general medical practice. Okay, so you do blood tests and you measure something like cholesterol or something, and 25 patients the samples were taken in a specialized hospital, and 150 patients, the samples were taken in the general practice. Question, does the greater number of consultants or doctors in the general medical practice result in a larger variance in the measures? So here, you see, we don't want to know whether the mean cholesterol is higher in the general practice than in the other one. We want to know whether the variability, maybe because they have more people taking the samples, is the variance larger in the general medical practice compared to the specialized hospital? So can you write down the null hypothesis and the alternative hypothesis here? So what's your null hypothesis and what's your alternative hypothesis?
The null hypothesis is the two of them are equal,
Yeah.
and the alternative is that the variance number one is lower than.
Very good. Okay. So now, because you know that, decide calculate the test statistic. Decide how you're going to calculate F0. So you calculate it, yeah? Ouais. Ah oui, pardon. Ah. Okay, what did you find then? Did you find 1.49? Yes. So, oops, where are? Now, one thing I told you right at the beginning when we spoke about the different distribution functions, I told you that Fisher doesn't have just 1 degree of freedom, it has 2 degrees of freedom. And the degrees of freedom are attached to what is at the top and what is at the bottom. So here, the first degree of freedom is the size of the sample at the top -1. So here it was 150 -1. And the sample at the bottom was 25. So 25 -1 is 24. So we need to go and look at the Fisher distribution function to find the threshold. Now, this is a bit complicated. So you look at this table. So at the top here is the first degree of freedom, K1, the one that's at the top. So for us, it's not called 1, but it's the one that's at the top. And this is the degree of freedom, which is at the bottom. So for us, it was 25. It's the other way around. Now, good question. Yeah, so it's the other way around. So I can find the tables again. What does that look like? Have you found the tape? Did I put the table somewhere? The table somewhere. Table statistics. Yeah. I just need to find the tables. Okay, here they are. So, if I do this, can you see? Yeah, you should be able to see. Now, so what did we say? 2449 and K1 is 149. So that would mean here and Yeah, this one. So it means that so yeah, and the way you read it, so okay, here we have it somewhere between 100 and 200 and 25 and 30. We can say it's 24. Okay, so somewhere between these two columns. And what are the four lines? The first line is 005, then 0025. So alpha equals 5%, 2.5%, 1%, 1. So here we are in the unilateral case. So we're looking at 5%. So it's between 1.8 and 1.7, so about 1.8. And the value that we had was, if I go back to the, so this means that, so this means that here you can replace it with 1.7, but we are still 1.549 is still lower than 1.7, and so we still do not reject the null hypothesis. Okay, so there is no difference in variance of measures between the two types of hospitals. So this is an example where you might be interested in the variability just for the variability. Now, if we go back to this example, which we did with the means, remember I said to compare the means, we should check that the distribution is normal and that the variances are equal. So now we did the we didn't check the equality of variances because we didn't know how to do it. Now we do, so we can check whether the variances are equal before we do the student t-test. So here, that was the true variance of the length of the operation. Is it equal or different? We're checking this in order to be able to do the test of comparisons of means. Does everyone understand? So in order to do comparing the means, you have to first check that the variances are not too different. That is a condition. C'est une condition d'application du test de student de comparaison des moyennes, c'est de vérifier l'égalité des variances. We didn't do it because we didn't know how to do it. Now we know how to do it. So here, we're checking, in this example here, this one, we're checking whether these variances, the real variances, are not too different before we compare the means. So we do the same, but use a bilateral two-sided alternative hypothesis. We can see that the variance of the second group is greater than the first group, so we do it this way around. So 1.56 is the test statistic, and we go and look for Fisher 1717 for 2.5%. So 1717, at least there we can't get it wrong. So it's between here and here, approximately. So around 2.6. And so here we can see that 1.56 is less than 2.6. So we do not reject the null hypothesis, which means there is no significant difference in variance, which means, can we do that student t-test or not? Yes, we can, because we're not rejecting the equality of variance. So it means we're allowed to do the comparison of means. So now, so we did this one. Okay, this was this, comparing variance for you have a problem?
Yes. I don't understand. Here it is lower, so reject.
Yeah.
But
No, we do not reject. We do not reject.
Okay.
So we're saying there is no difference between the variance. Yeah. And so this means that this line comparing the variance of two samples is the way you can check this condition, the red, it's a way you can check the green star condition, which is equality of variances, okay? And to do the Fisher's test, you also need to check that we have a normal distribution, so that we will see how to check it another time. So just remember that how to compare two variances using the Fisher's test, looking at the ratio, and Bartlett-Levine test is a way to compare more than two variances. We won't go into the detail of the test, but you need to know that it exists and that it's an assumption for an ANOVA. So what time is it? 1:15. So so we've looked at these 3 lines or columns and this one. So these we will not look at in detail, okay? But you just need to know that there are tests to compare variances for 1 sample and more than 2 samples. We will use them in software, but we won't work out how to calculate it. ANOVA we will see later because that's a bit more complicated. And now we're going to have a look at chi-squared testing. You feel up to it? 15 minutes of stats left? Yeah? Okay. You wish you were on Zoom so you could have a sleep, right? Yes? Oui? Ici? Yes, no problem. So it's a bit complicated because you have to, there's 2 degrees of freedom, okay? Remember, student, there's just 1. Here there's 2. So there's 1 which corresponds to the top and 1 which corresponds to the bottom of this, because here we calculate a ratio, un ratio, un quotient, okay? So there's a degree of freedom that corresponds to this sample and that one. So here it's N1 minus 1. Ah ben là, je me suis encore bourré dans l'écriture. So it's, sorry, here this is 2. So we have N2 minus 1 and here N1 minus 1, okay? So you take the size of the sample at the top, minus 1, and the size of the sample at the bottom, minus 1. C'est bon? And then you look for it here. So these lines are the first degree of freedom. So 14, 16, 20, etc. Là, c'est the other degree of freedom, 16, 18, 20. And then the 4 lines every time. So for instance, if it was 16, 16, si c'était 16, 16, on a 4 valeurs possibles. La première, ça correspond à alpha égale 5%. La deuxième, ça correspond à alpha égale 2,5%, etc. D'accord? And then what's a bit complicated is that because we don't have all the values, we've got 14, 16, 20, so we don't have 15, 17, tout ça. You have to kind of work out. So here it was 17, 17. So it's between that and between, well, that and that, okay? But you can see that the main thing is to get the right line, so 2.5%, okay? And then you can look at those 4 columns and you can think, okay, it's around, okay, between 2.56 and 2.76 à peu près. And usually the value you have to compare it with is a lot smaller or a lot bigger. Okay?
Madame, j'ai une question.
Oui.
Si on était en bilatéral, c'était bien la légalisation.
Oui. Ben non, mais de toute façon, là, on est en bilatéral. C'était le cas d'avant, on était en unilatéral. Là, pour... oui. So, so now we're going to look at chi-squared tests. So chi-squared tests are used for qualitative variables, okay? Well, I wrote discrete data, actually it's qualitative variables, data. Okay, so we're going to look at what happens when we have not quantitative data, but qualitative data. So it's different type of data. So we're going to look at what you call the chi-squared test. So this funny X is la lettre chi, which is the, well, I can't remember how many letter of the Greek alphabet. Okay, it's a Greek letter. And the 2 chi-squared is because we go up here on the squared. So we talked about the chi-squared distribution earlier on. So the general principle, when do we use a chi-squared test? We use it when we want to compare, either compare frequency to a theoretical value, or a distribution to a theoretical distribution, or compare different distribution or different frequencies. So we're going to look at the main question, and we'll just maybe have a first look at it, and then we'll look into it a bit in more detail next time. So to study the link between two qualitative variables, you must compare frequencies or proportions. So give me an example of a qualitative variable. We talked about it right at the beginning. Blood samples, A, B, O. So blood type, you mean, blood group, yeah. Color of the eyes, blue, green, black, whatever, orange, okay? You can have dichotomous variables, okay? So here, so just to start off with, so if you have a qualitative variable, such as blood group, if I want to talk about the distribution of blood groups in this room, I will have to say, can I say the mean blood group? No, I have to say there's 10% of blood group AB. So let's have a test. Do you mind? Is this personal data, or do you mind telling people your blood groups? Ça va? You'll survive? Okay. On les précautions. So how many people do we have blood group AB? Quite rare. None? Anyone on Zoom with a blood group AB? If you know, if you're not sleeping. Okay. So it's very rare, yeah. B? You don't have any Bs? Okay. A? A? Okay, thank you. And 0 and O? I'm O. Abdou, tu connais ton groupe sanguin? So, are you A, B, or O? You don't know. Some people don't know. You need to know your blood group. Okay, start again. A, B, we don't have any. B, we don't have any. A, quite a few. So how many is that? 1, 2, 3, 4, 5. We're doing to do percentages. And O, yeah. So some people don't know. Okay. Anyway, so you can see that we're going to say maybe 0% AB, 0% B. I don't know, 40 A, and I think it's more O, more A actually. But I can't remember. Anyway, 40 A and 50% B. If we have more than two categories, we have to give the frequency of each category to describe the distribution of the variable. Okay, we have to say 2%, 3%, 40%, etc. If we're looking at a dichotomous variable, such as okay, I hope nobody will be offended if I say man and woman. Okay, so if we have a dichotomous category, then we can say there's, for instance, 40% men, 60% women. Okay, so then, but we could just compare one category. If we want to compare the frequency of the gender in this room, I can say there's 40% women here, 41% in another M2, Masters 2 class. So we can just compare the frequency of women and we'll know the whole variable. Whereas if we want to compare blood groups, I have to compare ABB, A and O with ABB, A and O. Okay, that's what this is about. So either you compare two frequencies or all the distribution. And so the chi-squared test can be used in all the different cases, either comparing a frequency to a reference value or comparing two frequencies when you have a dichotomous variable, or when you're looking at distributions, you can compare distribution to a theoretical distribution or several distributions. And all that is done with a chi-squared test. So there's a general principle of the chi-squared test, and I'm just going to go over it once, and then I think I'll let you go because you didn't have a break, and I can see that everyone's kind of so we can go into, and we won't have time to finish anyway, so we can go into it next time. So just let me explain this. So the general principle is the same as other statistical tests. First, we define the null and alternative hypothesis. Then we deduce what is expected, the expected numbers under the null hypothesis. We compare the observed and expected numbers, and we conclude by rejecting or not rejecting the null hypothesis. So what you have to see is that the hypotheses in a chi-squared test are expressed in terms of frequencies, des fréquences, des pourcentages, but we use the numbers which come from the frequencies to calculate the test statistics. So for instance, here, if we say there's like 25% people who are group A, we don't use the 25%. We say it's 25% of, I don't know, 18 people. So that's 5 people. That's the numbers. We're going to look at the observed numbers, and then we'll say what would be the expected numbers if the distribution was this, that, or if we were comparing to another distribution. So then we're going to create tables like this with observed numbers and expected numbers, which we will calculate. And then when we compare the observed and the expected, we will see whether we are close or far away, and therefore whether we reject or not the null hypothesis. Okay? So we'll see that next time. Thank you. Bye-bye on Zoom. Thank you for listening and participating.